Hi guys, good afternoon. I'm R Umadevi, Faculty of Computer Applications from Bishop Weber College. In today's video, we are going to discuss about the basic concepts of deep learning. The topics covered in this session are linear regression, basic elements of linear regression, vectorization for speed, normal distribution and squared laws, multi-layer perceptrons, and computational graphs. So let us discuss these topics one after other. So to start with, we can discuss about linear regression and how it functions in machine learning as well deep learning. Linear regression is one of the easiest and most popular machine learning algorithms. It is a statistical method that is used for predictive analysis. Linear regression makes predictions for continuous, real or numeric variables such as sales, salary, age, product price, etc. Linear regression algorithm shows the linear relationship between a dependent variable and one or more independent variables and hence called as linear regression. So here we need to find how the value of the dependent variable is changing according to the value of the independent variable. The model can be depicted as shown in the figure. It has been given in a two-dimensional graph. So where x-axis denotes independent variables and y-axis denotes the dependent variable, and the line of regression is pointed along with the data points. This figure provides a sloped straight line representing the relationship between the variables, that is dependent variable and independent variable. So the mathematical representation of linear regression can be shown as y equal to mx plus c, which is the typical equation what we have discussed in mathematics. Alternatively, it can also be represented as y equal to a naught plus a1 of x plus epsilon, where y is the dependent variable, which is otherwise called as target variable, and x is the independent variable, which is otherwise called as the predictor variable, and a naught is the intercept of the line, which gives an additional degree of freedom, and a1 is the linear regression coefficient, which is the scaling factor to each input value, and epsilon is the random error. So we move on to the types of linear regression. So it can be divided into two types, that is simple linear regression and multiple linear regression. If a single independent variable is used to predict the value of a numerical dependent variable, then such a linear regression algorithm is called as simple linear regression. If more than one independent variable is used to predict the value of a numerical independent variable, then such a linear regression algorithm is called as multiple linear regression. So the linear line showing the relationship between the dependent and independent variables is called as the regression line. So a regression line can be categorized into two types. One is positive linear relationship. The other one is negative linear relationship. So if the dependent variable increases on the y-axis and independent variable increases on the x-axis, then such a relationship is termed as a positive linear relationship. The line equation will be y equal to a naught plus a1 of x. So which denotes the positive line of regression. Whereas the negative line linear relationship can be represented as shown in the figure. If the dependent variable decreases on the y-axis and independent variable increases on the x-axis, then such a relationship is called as negative linear relationship. The line equation will be y equal to minus a naught plus a1 of x. So in order to find the best fit line, so when we work with linear regression, Our main goal is to find the best fit line, which means that the error between the predicted values and the actual values should be minimized. The best fit line will have the least error. The different values for weights or coefficient of lines, that is A0, A1, gives a different line of regression. So we need to calculate the best values for your A0 and A1 in order to find the best fit line. So as to calculate this, we use this cost function. A cost function, otherwise called as loss function, is an important parameter that determines how well a machine learning model performs for a given data set. It calculates the difference between the expected value and predicted value and represents it as a single real number. The different values for weights or coefficient of lines, that is A0, A1, gives a different line of regression, and the cost function is used to estimate the values of the coefficient for the best fit line. The purpose of the cost function is to optimize the regression coefficients or weights. It measures how a linear regression model is performing. It can also be used to find the accuracy of the mapping function, which maps the input variable to the output variable. This mapping function is also known as the hypothesis function. The mean squared error, that is the cost function for linear regression, we use the mean squared error, that is MSE cost function, which is the average of the squared error occurred between the predicted values and the actual values. The MSE, that is mean square error, can be calculated using the formula 1 by n summation of I tends to 1 to n yi minus a1 of xi plus a naught the whole square, where n is equal to total number of observation and yi is the actual value, a1 xi plus a naught is the predicted value. Residuals are nothing but the distance between the actual value and the predicted value, which is otherwise called as residual. If the observed points are far from the regression line, then the residual will be high. So the cost function will be high. If the scatter points are close to the regression line, then the residual will be small and hence the cost function will be low. So next we move on to the gradient descent. Gradient descent is used to minimize the mean squared error by calculating the gradient of the cost function. A regression model uses the gradient descent to update the coefficients of the line by reducing the cost function. It is done by a random selection of values of the coefficient and then iteratively update the values to reach the minimum cost function. So next we move on to vectorization. Vectorization in natural language processing is the process of converting the text data into numerical vectors that can be processed by machine learning algorithms. It transforms words, phrases, or entire documents into a format that can be understood and processed by machine learning models. These numerical representations capture the semantic meaning and contextual relationships of the text, allowing algorithms to perform tasks such as classification, clustering, and prediction. Why vectorization is important in natural language processing? So there may be various reasons. So let us sort out some crucial reasons why this vectorization is important. The first one is machine learning compatibility. Machine learning models require numerical input to perform calculations. Vectorization converts text into a format that these models can process, enabling the application of statistical and machine learning techniques to textual data. The second reason is capturing semantic meaning. So effective vectorization methods like word embeddings capture the semantic relationships between words. This allows models to understand context and perform better on tasks like sentiment analysis, translation, and summarization. Dimensionality reduction. Techniques like TF-IDF and word embeddings reduce the dimensionality of the data, compared to one-hot encoding. This not only makes computation more efficient, but also helps in capturing most relevant features of the text. The last reason here is handling large vocabulary. Vectorization helps manage large vocabularies by creating fixed size vectors for words or documents. This is essential for handling the vast amount of text data available in applications like search engines and social media analysis. Improving the model performance. Advanced vectorization techniques like contextualized embeddings significantly enhance model performance by providing rich context-aware representations of the words, which leads to better generalization and accuracy in your NLP task. Facilitating transfer learning. Pre-trained models like BERT and GPT use vectorization to create embeddings that can be fine-tuned for various NLP tasks. This transfer learning approach saves time and resources by leveraging existing knowledge. So let us see the implementation of vectorization for speed. So while you train your models, we typically want to process whole mini batches of examples simultaneously. So here we can use an example in Python, that is PyTorch. So we instantiate two 10,000 dimensional vectors containing all ones. It has been depicted using two methods. So in the first method, we loop over the vectors with a Python for loop. In the second method, we rely on the single call to plus operator. Let us see one by one. In PyTorch, it has been given using the for loop. That is, here the content A and B are added using the for loop for I in range C of I equal to A of I plus B of I. In this method, it takes 0.17802 seconds to complete this operation, whereas alternatively, it can be reloaded with the plus operator to compute the element-wise sum. So here it takes 0.0036 seconds. So in the second method is dramatically faster than the first method. So only vectorization is preferred, which often yields order of magnitude speedups. So whenever we are handling with a very huge data, vectorization helps us to speed up the operations. So moreover, we need not want to write as many calculations, reducing the potential for errors and increasing the portability of the code. So hence we prefer vectorization. So next we move on to the types, that is stochastic gradient descent. We can represent this with a simple example. So imagine that you are trying to find the lowest point among the hills while blindfolded. Since you are limited by your touch, you can feel the ground immediately around you to determine which way is down. This is essentially what machine learning algorithms do when they are trying to find the best solution to the problem. So one of the most popular algorithms for doing this process is called as stochastic gradient descent, that is SGD, which finds the minimum of this function. It means that you have reached the best solution to the problem. This purpose of SGD, that is stochastic gradient descent, is an optimization technique which is used in machine learning to minimize the errors in predictive models. Unlike your regular gradient descent, which uses the entire dataset to calculate the gradient and update the model parameters, SGD updates the parameters using only one data point at a time. This makes it faster and more efficient for large datasets, although it can be noisier and less stable. Moreover, SGD helps to find the optimal values for model parameters to improve the accuracy of the predictions. So the main objective of using a gradient descent algorithm is to minimize the cost function using the iteration. To achieve this goal, it performs two steps iteratively. So it is given in this diagram. It calculates the first order derivative of the function to compute the gradient or slope of that function and move away from the direction of the gradient, which means slope is increased from the current point by alpha times, where alpha is defined as the learning rate. It is a tuning parameter in the optimization process which helps to decide the length of the steps. So it has been given here in the diagram, which may be clear. Types of gradient descent based on the error in various training models is divided into batch gradient descent, stochastic gradient descent, and mini batch gradient descent. So let us see one after the other. Batch gradient descent is used to find the error for each point in the training set and update the model after evaluating all training examples. This procedure is known as the training epoch. In simple words, it is a greedy approach where we have to sum over all examples for each update. Advantages of batch gradient descent includes it produces less noise in comparison to other gradient descents. It produces stable gradient descent convergence. It is computationally efficient as all resources are used for all training samples. Stochastic gradient descent is a type of gradient descent that runs one training example per iteration, or in other words, it processes a training epoch for each example within a dataset and updates each training example's parameter one at a time. As it requires only one training example at a time, it is easier to store in allocated memory. However, it shows some computational efficiency losses compared to batch gradient systems. Advantages of SGD includes it is easier to allocate in desired memory. It is relatively fast to compute than batch gradient descent. It is more efficient for large data sets. Mini batch gradient descent is the combination of both batch gradient descent and stochastic gradient descent. It divides the training datasets into small batch sizes, then performs the updates on those batches separately. We can achieve a special type of gradient descent with higher computational efficiencies and less noisy gradient descent. Advantages of mini batch gradient descent includes it is easier to fit into allocated memory. It is computationally efficient and it produces stable gradient descent convergence. The normal distribution and squared laws is given using the formula, that is the normal distribution with mean mu and variance sigma squared, that is standard deviation sigma, is given as f of x comma mu comma sigma, which is equal to 1 by sigma of square root of 2 pi into e power minus x minus mu the whole square divided by 2 sigma, where x is a random variable and mu is the mean and sigma is the standard deviation. Here in deep learning as well machine learning, this normal distributions and squared losses are used to minimize the error function. So next we move on to the next topic, that is perceptrons. Before going for multi-layer perceptron, let us see about what is perceptron. Perceptron is nothing but a simple artificial neuron having an input layer and an output layer. Then what does this neuron contain? So this neuron contains the summation function and activation function. So the input given to a perceptron are processed by the summation function and followed by the activation function to get the desired output. So it is given in the diagram here. X1, X2 are the input layer, followed by the weights W1 and W2. The summation function or activation function, that is your neuron, activates and it gives the output layer, where X1, X2 are the inputs, W1, W2 and W3 are the weights. So this is a simple perceptron. But what if we have many inputs and huge data? A single perceptron will not be enough right now. So we must keep on increasing the neurons. And here is the basic neural network having an input layer, hidden layers, and output layer. Based on the number of hidden layers, we classify it as a machine learning or deep learning. So here the neural network, we should always remember that a neural network has a single input layer, output layer, but it can have multiple hidden layers. So in the above diagram, we can see the sample neural network with input layer, two hidden layers and one output layer. So what is a multi-layer perceptron? So MLP, that is a multi-layer perceptron, consists of fully connected dense layers that transform the input data from one dimension to another. It is called multi-layer because it contains an input layer, one or more hidden layers, and an output layer. The purpose of a multi-layer perceptron is to model complex relationships between inputs and outputs, making it a powerful tool for various machine learning tasks. The key components of the multi-layer perceptron are input layers, hidden layers, and output layer. In the input layer, each neuron or node in this layer corresponds to an input feature. For instance, if you have three input features, the input layer will have three neurons. And MLP can have any number of hidden layers with each layer containing any number of nodes. These layers process the information received from the input layer. The output layer generates the final prediction or result. If there are multiple outputs, the output layer will have a corresponding number of neurons. So in the diagram, we have input layers followed by the hidden layer and the output layer. The activation function. The main purpose of the activation function is to convert the weighted sum of the input signals of a neuron into the output signal. And this output signal is served as an input to the next layer. Any activation function should be differentiable since we use a backpropagation mechanism to reduce the error and update the weights accordingly. The types of activation function includes sigmoid, tanh, and ReLU. Sigmoid function. It ranges from 0 to 1. A small change in x would result in a large change in y. Usually it is used in the output layer of binary classification. So generally sigmoid activation functions can be used for binary classification. The tanh ranges between -1 and 1. Output values are centered around 0, usually used in hidden layers. ReLU, which is otherwise called as rectified linear unit, it ranges between 0 and max of x. It is computationally inexpensive compared to sigmoid and tanh functions. Default function for hidden layers, it can lead to neuron death, which can be compensated by applying the leaky ReLU function. So far we have discussed about the multi-layer perceptron and the activation function. So now we move on to the working of a neural network. A neural network works based on two principles, that is forward propagation and backward propagation. So let us understand these building blocks with the help of an example. So consider a single input layer, a hidden layer and an output layer to make the understanding a little bit clear. So in this we have an input layer where x1 and x2 are the inputs, w1 and w2, w3 are the weights used by the hidden layer, and the output layer is shown here. So considering we have the data and would like to apply the binary classification in order to get the desired output. So take a sample having features like x1 and x2, and these features will be operated over a set of process to predict some outcome. Each feature is associated with a weight where x1 and x2 are the features and w1 and w2 are weights. These are served as an input to the neuron. A neuron performs both functions, that is summation function as well activation function. In the summation, all the features are multiplied by their weights and bias are summed up. It is y equal to w1 into x1 plus w2 into x2 plus b is nothing but the bias. This summed function is applied over an activation function. The output from this neuron is multiplied with the weight W3 and supplied as an input to the output layer. The same process happens in each neuron, but we vary the activation functions in the hidden layer neurons, not in the output layer. So we just randomly initialize the weights and continued the process. There are many techniques for initializing the weights. So it is done with the help of back propagation. So back propagation uses chain rule to update the weights. The chain rule is nothing but it provides a technique for finding the derivative of the composite function. The number of functions that make up the composition determines how many different uh, functions are necessary. For example, if a composite function f of x is defined as, then the chain rule will be like this. Let us apply the chain rule to a single neuron. The ultimate goal of your neural network will be to reduce the error in order to make it possible to update all the weights through back propagation. We need to find a change in the weight such that the error should be minimum. So in order to do that, we calculate dE by dW1 and dE by dW2. So considering the summation function S, which is equal to x1 w1 plus x2 w2, and activation function, that is your sigmoid function, using the formula e power x by 1 plus e power x. The chain rule can be applied as follows, that is dE by dW1 is equal to dE by dA into dA by ds into ds by dW1, and dE by dW2 is equal to dE by dA into dA by ds into ds by dW2. So that's how the forward propagation as well backward propagation is applied in order to obtain the output. So once if you have calculated the changes in the weights concerning the error will be updating the weights using the gradient descent process. So the new weights are calculated using the formula W1 of new equal to W1 of old minus zeta of dE by dW1, and W2 of new equal to W2 of old minus zeta of dE by dW2. So ultimately, forward propagation and backward propagation will be continuous for all the samples until the error reaches the minimum value. So the last topic we are going to discuss here is about computational graphs. Computational graph is a way to represent a mathematical function in the language of graph theory, where nodes are connected by edges and everything in the graph is either a node or an edge. In computational graph, nodes are either input values or functions for combining values. Edges receive their weights as the data flows through the graph. Outbound edges from an input node are weighted with that input value. Outbound nodes from a function node are weighted by combining the weights of the inbound edges using the specific function. So let us depict this using a simple example. Consider a simple expression f of x, y, z, which is equal to x plus y into z. So this can be expressed as a computational graph as shown in the figure. So here the nodes are represented. There is x, y and z are the nodes, and plus and star operators are nothing but your functions. So which can be depicted as shown in the figure. So this is how we represent a computational graph, which helps to reduce the equations in deep learning. So thank you guys.